Hello, my year 11. This video is about chapter 5, 5.1, electric field. So before we start, I want to let you know that I will expect you to get this file like how we do in the lesson. So the best is if you can print it out. If not, then see if you can try to write on this file. Better to write rather than type, because ultimately when you do the exam, you would be writing in the exam instead of typing. Okay, so I'll send you this file and please try to work it out. So let's stick with the textbook first. So I would want you to read this page 196 and also up to 197. Alright, so you may want to pause the video, try to read through the paragraphs until I think up to here, and you can, after that you can continue the video again. Okay, so let me reiterate some key points to you. So first of all, we are talking about electric field. In chapter 6 or even earlier, you learned about gravitational field, and now we're talking about electric field, and it's something that you have already learned in year 10, but then we will try to make it more quantified. That means we have to do some more calculation in IB. Okay, so for electric charge, so first of all, I think very basic things like, you know, there are two kinds of charge, positive, negative, and they may repel or attract to each other depending on the situation. So the force could be attractive and repulsive. So that's why for electric field, the field lines is always going from positive to negative. So this is something that you have to remember. For gravitation, it's always easy because it's always going towards the mass, because it's always attractive force. So this is the difference. And I think these are all some history you may want to take a look. And so for the properties, I think that should be all right. And something interesting to take a look is there's a word called quantize here, and you will see this word again in chapter 7. And basically, if you study chemistry, but I don't think anyone here study chemistry, if you see this name, this is something to do with quantum physics. So if you heard about quantum physics, you know it's something that is very strange, very difficult to understand. But the word quantize here actually means is discrete. I want to say concrete, discrete. Okay, so that means it's not continuous. Basically, it's the opposite word of continuous. That actually means you can say for charge, we always have either 0, you may say 1, 2, 3, 4, etc. of number of charge. So you never have something like 1.5 charge. That is not possible. So that is called quantize. And since, if you remember, in year 10 we learned about a word called Coulomb, or is a unit of charge, where if you can try to look up the data booklet, let me show you, data booklet, you can find the number here. Okay, so it tells you that for one electron is equivalent to that many of Coulomb. Okay, so you can work it backwards to find out how, like, 1 Coulomb represent how many number of electron, or you can use it to describe proton too. Okay, so here's a number. You can rely on the data booklet. Okay, so there's another thing called conservation of charge, which is very common, like it's basically common sense. Here is an example. You can try to work in the booklet later on. I'll give you some time. If you want to work on it now, you can pause the video, and we'll talk about it later. Okay, but then here we also have another some keywords here, like for example lattice, and this is a structure proposed actually by the chemist and referring to some solid metal. So for example, if you try to search the word lattice on Google, then you will find out something like this. So basically it's a gigantic, it looks like something like this, like they put the bondings between them, and this is how people theorize the matter. And lastly, we also talk about the conductor, electrical conductor. The reason why they are conductive is because they have mobile electron or free electrons, and while insulator, that they don't have many. All right, we don't say they literally don't have, but they don't have as much free electron. So sometimes people may use the word to explain, to describe how it is so many, so they use the word sea of electrons, sea of free electrons in that case. Okay, so I'm going to explain the word example now, and if you haven't done it, please pause the video, try first. Okay, so for 5.1 it's actually very simple. So the question is saying that if you have two conducting sphere which of 4 mu Coulomb and negative 12 mu Coulomb, and they are simply allowed to touch each other. So that means, if you recall what you learned in year 10, this method is called conduction, similar or even exactly the same as the conduction in thermal, but now is static charges. So basically what you have is 4 mu and then another one that is negative 12 mu, and then so when they separate again, before they separate, apparently they would become neutralized for some of the charges. So you know that if 4 minus 12, that actually makes negative 8. So each of them should have negative 4 as they try to spread out by themselves. So each of them will have negative 4 mu, and that is the number of charge. And I would say the answer is negative 4 mu Coulomb. Alright, this is the unit. Okay, so back to our textbook here. Here is something interesting, even though may not be relevant to your exam. It's called the Tolman-Stewart experiment. Think about this. If you haven't read that, think about this. How do people know that the electron, if you recall in year 10, we said the electron can move freely while the proton or the atom are fixed, they cannot be moved. How do we actually know, right? So one way of doing it, or to do experiment, is you can try to think about it, and the way that this previous scientist did, apparently these two guys did in I think more than, how long is this, more than 150 years ago, was trying to accelerate. It's very, very smart way to do, is to accelerate a piece of metal, I believe. Okay, a piece of metal. So imagine that if you have like a toy car like this, and inside the toy car there are something that can be moved freely. So what you can do is, if you try to swing the toy car or try to push to accelerate the toy car, what happens is those free to move billy balls inside will go backward because of the inertia. So that's why you see this picture is a very good illustration. Those things that are kind of pushed backward are the electron. They find out. The way that they find out is by using, I think the way that they find out is using something called the Hall effect. But this is not in the syllabus right now. But the way it's working is something to do with applying electrical field and also the magnetic field at the same time, and then they can somehow measure the charge inside at the back. So then they can know which one is free to move. So it's very smart way to do. Okay, so here finally is something that is more directly related to your exam, if you are looking for that, and that is how to calculate the force between the two charges. As we said, there will be attraction force or repulsion force between the two charges. So how do we calculate the forces by this? And if you wonder why I show you or I teach you this chapter after chapter 6, if you remember, chapter 6 is about gravitation or circular motion, then you should quickly recall there is one equation that looks very similar to this. Let's take a look at what this is first. Okay, so first of all, this equation, there is a name, it's called Coulomb's law. Okay, Coulomb is a scientist's name, and that describes the electrical force between the 2-point charges Q1, Q2 respectively. Apparently its force and its action and reaction pair according to Newton's third law. So no matter you're talking about these charge giving a force to the blue one or the other way around, these charge giving a force to this one, it's all the same. And so the way to calculate this is by multiplying the charge number times k. K is a constant. Did they mention that? No, actually they did not. Okay, they mentioned here k is a constant, which is equivalent to this 1 over 4 pi epsilon over here. Okay, so it's just a constant. Divide by the r square. So r is a distance between the two charges, like here. Okay, the distance between two charges. If you try to look at this one and recall what is similar in chapter 6, and that should surely be the force of gravitation, which is F equals to big G times m1 m2 over r square, and you will find the symmetry of electrical field and gravitational field. And this is the best thing that scientists find out, because they actually believe, because of this, they believe that the universe in itself is symmetrical. Because if you look at the whole thing, is very neat that both force would decrease with inverse square of the distance, separation distance. And also for electrical force is something to do, of course, with their charge, and for gravitational is something to do with their mass, and they both multiply with a constant. Okay, of course they are different constants. So that's why we'll learn about this chapter after the chapter 6 in mechanics. Okay, so the way that you apply is in fact very similar to what you learn in chapter 6. So let's try to do some exercise. Okay, so for the constant here, which is equivalent to this number, and you can also find in the data booklet. Let me show you. So that should be here. You can see 8.99 times 10 to the power of 9. That is k, which is, this is the equation that you have. So you don't have to find out the pi and epsilon. You can still find it, but then you can just use k, that one directly. Okay, for this one, you may find it useful in the future, but not now. Okay, you can just use k directly. And that's it. Okay, for the work example here, I want you to work on the booklet. Oh, actually it's not here, so I think we can just talk about it directly. So it said we have graphite that is 12 times larger than that of vacuum. So basically you use the equation of that, and then the difference is simply the permittivity of vacuum is 12 times larger, so you just substitute into that, and then you find the force when you change the material. So the epsilon here is something to do with the medium itself. Okay, so this is an example. I don't think it's that important, so I think I skip it in the notes. So for now, I would want you to do 5.3 and 4 here, and then pause the video and we will discuss it very soon. If you want to recall what you have done in year 10, I recommend you to watch this video from this teacher. I think Bruce is very good at making some video and is all interesting, and in fact most of these are actually shown similarly in year 10 lesson as well. So it may be a good time for you to watch a video and just to revisit what you have done in year 10. Okay, let's take a look of this question. So we have two charges and they are both positive. Okay, if they don't say that, then we assume it's positive, and there's a distance between them. Calculate the force on each charge. So basically you just have to apply the equation that you learned, which is K Q1 Q2 over R squared. And what you have to do is simply substitute all the things that you know. For K, let's take a look again. 8.99. So 8.99 times 10 to the power of 9. And then Q1 is 2. Mu is actually 10 to the power of negative 6. If you don't remember, you can try to double check that with your data booklet, which is here. Okay, micro. So negative 6. So negative 6 here. And then also 8 microcoulomb, if you like to say micro, that's fine. And then for R, you can put 3 square. But if you do it this way, be careful, then you get it wrong, because if you look at the unit, it is in cm. So what you have to do instead is you have to make it the SI unit, because if you remember how we do normally, force is in Newton. And in fact, if you look at these constant from the data booklet with its unit, then you find out that it's also in Newton, meter, and Coulomb as well. So that's why you need to keep it as SI unit for all of these. So these are fine, and you're just missing the distance. So you have to convert cm to m, which is 0.03 bracket square, or you can divide by 100 if you want. Okay, so I will leave the rest to you. It's just pressing the calculator. You should be able to find the value. For part B, it said the charge increased to 4, so it was Q1, it was 2, now increased to 4. Determine the force on each charge now. So basically you could of course go through this whole thing again, but it's actually not a smart way to do. The smarter way to do is simply knowing that, since if you look at this equation, if the Q1 double times 2 and the rest of them remain the same, then F in itself would times 2, of course. So what you can say about is you can simply grab the answer from part A and you just multiply by 2 in that case, and that will be the same force for both of the charge, because like I said, it's action and reaction pair, and you can see it from the equation as well. So the force is simply times 2. Again, in the exam you want to show the exact number. Okay, for next question, let's take a look. It said there is a positive charge line joining this and this with the previous example. Determine the distance from Q1 where the third positive charge experience is 0 net force. Okay, very interesting question. So what you will want to do is you should surely draw a diagram to let yourself see better. So what you can do is you can draw Q1 and then Q2. Notice that they are both positive. Positive 2, positive 8. I'll ignore the unit just for simplicity. And then there should be one more charge in the middle. Let's call it Q3, so that when, well, of course it's positive also, so that both of them will repel from each other. So imagine that Q1 and Q2 are fixed, of course, right? They cannot be moved. But then Q3 is staying there, experiencing the force between them, and Q3 will experience a force from Q1 which push to this side. So let's call it F1. And Q3 also will get a force from Q2 which push it to the left. Let's call it F2. So when Q3 experience 0 net force, that is when these two forces are the same. So what you can say about is and you want to know the distance, right? So let's make a number. you know it was 3 cm, so in total it was 3 cm, and let's call this x. And so in that case, you don't want to make a new variable y, but what you can do is you can say it is 3 minus x, or even better is 0.03 minus x to keep x as meter. Okay, so let's try to construct equations. So since you know the force is 0, so F2 equals to F1, which is K Q1 Q3, because we're talking about this one for F2. Is it? Oh, actually no, it's actually Q, because F2 is exerted by Q2. F2 exerted by Q2 to Q3. So actually I should, if I have to match it, then I should write this, but in fact it actually doesn't really matter a lot. So 0.03 minus x bracket square, same here, K Q1 Q3 x square. Okay, I should have given you more space, sorry about that. So first of all, K cancel out, Q3 cancel out, so actually the amount of charge of Q3 doesn't really matter. And so you have Q2 as 2, wait no, 8, and then Q1 as 2, because if you look at the diagram, okay, so this is why you want to draw a diagram. And then you have x square, and then 0. Okay, well, don't have enough space. 0.03 minus x square. Okay, so you just have to solve it, and you should be able to find out the number of x. Okay, so I will leave the job to you. This is just some math calculation. Okay, so you can find the answer from the textbook if you want, or I can show you here actually. Yeah, let me just show you here. Okay, so this is this is how you could do it, and that's all for this part.